All right, so CO230 week 3, and in this particular chapter we are going to talk about data and signals. Now you've read the chapter already, okay, which is great. You've read the chapter already, and you probably noticed that there's a lot of technical terms in this chapter. Okay, we will talk a little bit about how data is stored. We'll talk about how data is transferred. But there are a lot of places that if you have a highlighter, you could basically highlight in order to come back to it later on. Okay, so that's something you can do in your textbook. Let's start though to talk about waves. Okay, waves are very common in our experience. When I speak, I create waves in the air, and then you can hear me. Right, your ear is going to move pieces inside, and then your brain is going to understand that. What's going to happen if I remove the air from the classroom? All right, the waves are not getting to you anymore because the media was removed. Okay, now consider maybe Star Wars and some of the explosions that take place there. What happens through the audio speakers when that happens? Yeah, you have all this noise going on, right? When in fact there's no air to carry that. That's the one thing that's not realistic about Star Wars. Right, right. Well, there may be a few other things about Star Wars that are made up. Okay, so waves in the air. But there are other types of media that allow us to transfer waves through space, for example, and those are electromagnetic waves. You see, those can travel in space. So let's talk about wave to start with. Okay, a wave is a very natural occurrence, and a wave has something called a wave is going to have a length. Okay, waves oftentimes also have this unit of a hertz. Anybody knows what a hertz would be? Hz, please.
1 machine cycle per second.
Okay, 1 machine cycle per second. So in a CPU, in a computer, you might have 2 gigahertz CPU. It can perform 2 gigabillion operations per second, right? All right, so a hertz is when a wave makes a full turn in 1 second. Okay, that's frequency of 1 hertz. So if you have 5 hertz, 10 hertz, you squeeze more and more of the movement into 1 second at higher frequencies. Well, let's talk about the piano for a moment. And does anybody play the piano? You play the piano? Can you draw a grand piano on the board? Would you be comfortable doing that? Go ahead. Go ahead. Yeah, just like the bird's view. Yeah. No, not the key. You don't have to draw all the keys. There's a lot of them. Just draw the general view of the piano. Like if you were looking from the top down. Just the outside structure.
Yeah. All right. All right. Specify it for the keyboard. Not an artist. So.
That's all right. Well, you are. You said you'll play the piano. Okay, so these are the keys, okay, and then, okay, is that a grand piano then?
It's supposed to be.
Supposed to be? Okay, all right, thank you. All right, thank you. So, anybody else, any suggestions, any improvements on this design? All right, come over. Would you like to come over and draw it in? All right. Well, you're not wrong. The bottom idea is that there's so many designs for a piano these days that Okay, yeah, thank you. Very good, yeah. So what we have on the piano is, and the first element is longer than the other one, right? Now, why in the world is that? Yeah, different frequencies are required. We want to have low keys, high keys. So the strings on this side are much longer than they are on this side right here, right? Let me see if I can grand piano images. And so, yeah, so you can see that the strings on the inside here are longer than the strings down here. So longer strings are going to have lower frequencies, lower sound to them, because they have more length here to vibrate. Okay, so lower frequencies versus so the lower frequencies on the grand piano would be about 30 hertz versus when you play the high keys with the short strings, so that they're going to vibrate much faster, those would have about 4,000 hertz. Okay, and this is a range that we can hear. Now there are waves that we cannot hear. They go beyond here. Maybe you seen the little whistles for dogs, right? You can hear, or some people can hear them, some people can. So basically, the waves that are produced, audio waves, there's a range that we can hear and a range that we cannot. But visualize, whenever we talk about waves, visualize that string and the fact that all waves have this kind of behavior and then properties. Something can be loud. Okay, so now we're making the string extend further, therefore the amplitude of the wave is greater. Okay, or if we play it very soft, the amplitude is low. It doesn't change its frequency. You see, it's still the same sound. Still the same sound. So the properties of waves, like the amplitude, like the frequency, they are going to depend on how long the string is, how long the specific frequency is. So that's a good introduction. And if you can imagine a ripple in the water, that produces a wave as well, right? So all these very natural elements are based on the wave. One thing that's interesting in terms of having a nature of a wave would be light, right? We're not sure whether light is a wave or is it a particle. We know that it travels through space, so it shows certain properties of a wave, but it also can, for example, push an object. And so it has photons, the particles that can actually do things. Most other waves can be easily identified. So we have physical waves, we have electromagnetic waves, and now these waves can go inside of a cable, or we can have those waves in a wireless media, in a wireless environment. Okay? But the principles will be the same. We're going to have a certain properties like frequency that will go across all of them. Well, that's good. Let's take a look then at a process called digitization. Because the analog wave, the natural wave, it is very, very common in the universe, very common in our lives. When you see a picture, maybe Mona Lisa, that's drawn, you have infinite number of shades that you can see on an oil picture. Or when you play an instrument, maybe a violin, you have an infinite number of sounds that you can make as your finger is making the string shorter or longer. Those are properties of an analog wave, infinite set of possibilities, and artists love that. Now, when you come to digital world, our task is very difficult, and that is, how do I make from a perfect picture, perfect piece of music, how do I make zeros and ones, which is great for storage and great for transmission, but somehow we have to make it less perfect. We have to, in a way, we're going to chop it down and take some of that quality down. And here's why. in the process of digitization, you might take the approach of sampling, and that's where sampling rates come from. So if I was to take this perfect wave and turn it into digital signal, I would say, okay, we start right here, then we go here, then we go here, and the amount of points that I am making here, and I'm just eyeballing the wave, the amount of points I'm making on the wave, I'm choosing the points, they become a digital representation. These are my samples. The more samples I take, okay, the more samples I take, the more accurate my representation will be. Because from then on, the opposite process, you start with digitizing the analog wave. Once you have digital, I want to get my real picture back. I want to get my real music back. A computer program has to come along and make sense about what happens between those dots. And so the computer program, a codec, is going to go in and say, okay, so let's just connect it this way. Let's maybe make a little arc here, right, and a little arc here. And that's what you end up then through the process of modulation, where you will recreate whatever was saved. Now this is a very rough draft, right? So what you end up having is sample rates would be in many thousands. Okay, so per every second, you end up sampling either the picture or you sample the music. And so when the dots are connected, when you hear the music come from a digital source like a CD player or maybe a computer, it actually sounds to us like a real picture. So what saves us in this digital world is that our senses are fairly easy to trick. You look at a moving picture that has 32 frames per second, and it looks to us like it's a real world, right? Like it's actually happening, right? Now, in analog wave, you have infinite set of frames, whereas we are just fine with 32 per second. If you listen to music, it is not the same. The digital music is not the same, but it has come to such a high sampling rate, then to our ear it's perhaps indistinguishable. You look at photography, right? We used to do that with film. It was developed, and it was analog because you had infinite set. When the line was round, it was really round. Now, of course, we can have a very high capacity for sampling, but sooner or later you have basically pixelation, because suddenly you have the samples that were taken and what's in between is lost. All right? So the process of digitization and then process of modulation. And in fact, there is another way to modulate. What I showed you here was sampling and then modulation based on postcode modulation. But on page 57 in the textbook, you have the delta modulation, which is a little bit different approach. Instead of sampling, okay, we are going to assume that we can take our ones and zeros and actually have a representation of that wave. So the computer just needs to remember, go one down, one down, one down, one up, one up, one up. And that works okay until you have to move enough data so that the actual analog wave has too high of a frequency, and as you can see towards the end of the figure 2-24, you end up with a distortion of the digital signal. All right, so different ways of going from the ones and zeros back into the analog view. So at this point, let's just take a few minutes, 5 to 10 minutes, on the project sampling rates. Okay, go ahead and select it, and then use the textbook or use the web browser to research what sampling rates are matching which media, and we'll resume momentarily. So now let's talk for a moment about why the digital waves sometimes are better than the analog. Okay, previously, you know, it was pretty clear that the real wave, the analog wave, is great. So playing a real cello is much better than maybe playing it on a synthesizer, even though the sounds are close, the same. So why do you think that we went from analog television to digital television? Please.
It's easier to transport, so you can allow multiple things, with multiple transmissions at the same time.
Okay. Okay, now having said that, with analog wave you also had multiple channels you could go through, right?
So as in one station broadcasting more than one channel.
Okay, all right. So that
Oriented wave, basically, that allows more from one signal than just multiple digital signals.
okay, so when the wave is digital, you can put more different things, and you can use then software to a software upgrade would allow you to do more. Yeah, those are good qualities of it. Any other reasons why we would want to go to digital television instead of analog?
Government wanted to put it.
All right. So government conspiracy. There's and some folks feel that you know, the push for technology. Here we have all these televisions, and we need a high quality signal for them. So the government says, everybody needs a new television set, and so that might be a reason. Who knows? But think about this: if a government was to actually have a good idea, a good reason to switch to digital television would be the quality of the reception. And why would that make any difference between an analog and a digital wave? Well, the difference is this: when you use an analog wave and you send it out over some period of distance, okay, this wave is going to be subject of multiple issues, like noise, like obstacles, physical obstacles. And what's going to happen to this wave is when it arrives at a house in a valley somewhere, this wave is going to look much different, okay? Sometimes it is disturbed to such a degree that you just have snow on the screen and you can't see the screen very well. And it'll have a range. See, this is the analog wave, and we don't know which element here is noise and which element is just the change of the signal. Which is why it was common with analog television. If you live close to the station, you were fine. But further down, even when you tuned to the right place, a little bit of the picture was not right. Now, why is it different with the digital signal? Well, because when you send simply ones and zeros across, okay, so let's say this is a 1, this is a 0, this is a 1, this is a 0. When you do that, and now the same noise, you have the same mountains, same obstacles, and same microwaves around. So now when you add noise to that, okay, now when you add noise, you can actually figure out much easier what's a 1, what's a 0. And this is called the noise filtration, right? So you can, and all you have to do, you don't have to know anything in between, you see? All you have to know, does this look like a 1? Yes. Does it look like a 0? Yes. Which is why the picture can be clear over long distances, and the quality of the picture can be, you know, high def and so forth. You can send more data because we can have more reliable connectivity. All right. And so in the textbook, this is illustrated here. We have a digital wave. A 0 at the bottom and 1 at the top. 0, 1, 0, 1. And when you add noise to that, the noise is present. Can't get around that. But you can easily see what is a 1 and what's a 0, and that is the huge benefit of the digital television versus the analog television. And for comparison, if this is the original analog wave, and now you add noise to it, you can see how easy it may be to confuse noise with the actual change in the analog wave. And so that's why it was difficult to keep the quality of the reception, which is also then connected to how much data you can send. Therefore, you can't send the high def as far. You can't have multiple channels or programs on a single channel. So the digital signal is definitely of great benefit. And in a digital signal of this sort, you can put a repeater somewhere so that this cleaning up of the noise can be done middle way somewhere. You straighten out these waves, and then you can send them even further in a very good quality condition, okay, so that they arrive further down. Yeah, so the digital versus analog signal. And here's just an example of, even in the digital signal, at some point when the noise is just high enough, you truly cannot tell what's a 0 and what's a 1. So sometimes when we send data from one computer to another, okay, some of this data might be lost, which is why, and thinking back to our OSI layers, higher layers would have protocols, and those protocols would then determine whether something has to be sent back or resent, right? Because even in digital world, the noise sometimes can be very, very high. And noise, can be multiple things. It could be a wire that you rode over with your chair, okay? You take your chair, you're sitting on it, and maybe you step on the wire just the wrong way, and now the connection isn't clean, or maybe the insulation on the wire is not working correctly. And this is going to cause this kind of a noise on the signal itself. So when we talk about signal, imagine for a moment a train. Anybody familiar with Thomas the Train? Got kids? All right, Thomas the Train. My boy, he just loves that stuff. So train is the signal. Some trains are faster than others, all right? And in certain environments, so let's say that you have a cable, the signal can go really, really fast, versus if you have wireless, there are some limitations to this media. So that's our train, and now the data is what goes inside of the different carts and troublesome trucks and such. So you then can manipulate. Once you have the train going at the speed of the limitation of your media, you can still send more data because you can compress more data into the carts, into the train. And so we'll talk about that, how there are ways to actually put more and more data. And the beauty of digital signal is that the particular train that you're sending, it didn't have to be the same channel, the same information. But the train could carry one cart that belonged to maybe channel 1 and one cart that had a piece of data for the next channel. And so you could, over the same media, send all this different varied data. But it was, in fact, separated, and it could be compiled and composed again at the end, at the reception end. So the digital signal has very many good properties that we take good advantage of. Yeah, let's for a moment switch to the next issue here. Let's see. Yeah, this is a good representation of what I just drew earlier, and that's the frequency. In a 1 second period, that's single hertz, and here's a wave of 2 hertz, so you have 2 full lengths of the wave within 1 second, and this is the idea of a frequency. This has nothing to do with how loud the sound would be, right? The loudness would be managed by a different property, and that property is right here, where we have the same frequency, but the amplitude is higher. right? So in your car, you may have an amplifier in the back, right? That's what it does. It basically allows you to take a wave and stretch whatever the signal is to have really high amplitude. Which is why you can imagine that high amplitude information is going to be easier to receive on the other end, right? Low amplitude, if you speak very softly, it may not be received very easily. Old people, you got to speak really loud. So you have these waves and it's easier to move around the broken parts in the ear. All right. Let's talk for a moment about transmitting analog data with analog signal like a carrier wave. Okay, carrier wave. When you are in your car and you tune in via FM, you tune into a specific frequency. Okay? That frequency, maybe 101.5 or something of that sort, that frequency is a carrier wave, and on top of that carrier wave, you actually have another set of waves that are the waves of the music or the signal that the speaker is transmitting. And so here's a nice picture of how this happens. If this is the audio, the music on the radio, and this is 101.5, then this is what happens on for your radio to actually receive the signal and you be able to tune in. You tune into the carrier wave, and then your radio is able to discern what other signal is being carried on that carrier wave. Okay? And there are two ways of receiving the signal from the carrier wave, either through modulation of frequency, so the wave is getting longer or shorter, or you can manipulate the amplitude of the wave. So like it is in the picture right now. The same frequency of a wave, but it's getting larger or smaller, and out of the tops of it, we can see what the speaker is actually saying. Therefore, on your radio, you find FM, frequency modulation, or AM, which is amplitude modulation. So the idea of a carrier wave that can carry the signal. All right, let's. All right, so here's an example of sampling. This is the postcode modulation, and again, modulation is how you actually put the data back into analog form. So we already have the points, the samples that we took, and now it's up to the computer to recreate the rest of the wave, and you can plainly see that it's more of an art than science. So companies like Sony, okay, are going to create software that's able to take the high-def signal in your computer, and you might be familiar with the Bravia engine. They create the software, and they pride themselves in saying that between these points that any television can receive, we have this artistic ability to discern that the wave can be just perfect. And it's going to be more realistic and more what was actually filmed than other companies. So that's the edge that companies get via software. You can see the very top, right? The original form goes really high, but the digital signal has no trace of that anymore, because within the sampling, that part was missed. Yeah. Excellent. And so you can see that as you increase the sample rate, the space for the actual stipulation and figuring out artistically is much smaller. So at higher sampling rates, you do have a more realistic signal, and that will be common with vendors that do not put as much research into it. Okay, that sounds good. One of the key words that was explained in this chapter is called attenuation. Anybody familiar with what that might be? Attenuation? All right, go ahead and look in the textbook, and you can look in the glossary in the back. But let's do a quick look at what attenuation might be. Just a moment. So you found the answer? Awesome, awesome. All right, go ahead and check check on that, please. All right, and so now that you found what attenuation is, how do you explain that? What is attenuation? Please.
A way of rating actual loss of the signal or degradation of it.
Okay, and what would be the opposite to attenuation? Amplification, right. So attenuation is just a fancy way of saying we're losing signal. And this is going to happen if you have a wire that's very, very long, right? As you have your cable television installed, okay, the folks are sensitive to that, the installers. They know that you can't just have wire and wire going around the house because the quality is going to, quality of the signal is going to be affected. So attenuation is just the process of naturally losing the quality of the signal. And this is actually independent of other noise. So if you have additional noise on the wire, maybe your TV cable is going next to your microwave, right? And then you see you're losing picture every time someone puts a pizza in there. So other noise is going to be independent of attenuation. That's just a property of media that would take place. Okay, so let me ask you a question about this one piano that I like. Here is a piano that that basically represents a little bit of a technology element. It's from a little place in Florida. Let me change that here. All right? And so I want you to look for this answer. Is this piano giving us digital signal, or is it analog? Okay, is it digital music, or is it analog music? Let's listen to this guy for just a moment.
Hello, my name is Russell Housen with the Piano Outlet here in Margate, Florida. Today we just received a beautiful Wurlitzer 80-gram piano with a 5'8". It was originally purchased new in 2003. This piano was offered by a local Baldwin dealer, and at that time when this piano came out, it was being manufactured by Young Chang in Korea. So this is a Korean piano, not Chinese, because today's Wurlitzers aren't as good because they're manufactured in China. If you know anything about Chinese pianos, they're really not the best. Anyway, this particular piano has had very little use whatsoever. It came out of a home. They did not play the piano in the home, it just uses furniture. And this particular piano comes with a beautiful player system made by Baldwin called a concert caster. It's really neat because it plays CDs, it plays floppies, it also has an internal memory. This is the wireless remote. It's full function. You could access the record feature. You could access the sound module if you wanted to play other instruments along with the piano. And you could also access the library. For instance, it has an internal library, so we would want to press internal library, press play, and then just play it. You can go to the next song. This is an original artist series CD by QRS where it's the original albums of certain recording artists with the piano playing along with it. Let's try it. piano. For instance, if I wanted to play, well, first I'll play the piano by itself. And then I'll play it with some more instruments in the background. Let's play some Mozart. First, the piano by itself. Now I'm going to add some strings to it. I'm going to turn it up a little bit.
All right, so with this in mind, what would you say? Is this digital music or is it analog music?
It's analog.
All right. So you say analog, based on.
The actual strings being played.
Okay, yeah. So the strings are in the piano, and then when the keys move, the actual strings are played. Yes. Yep. Now you said both.
Also both the other instruments that play too.
All right, yeah. So for a moment there was this catchy tune, and there was some drums, some bass, and there were strings here, which were not actually created through vibration of strings, but they were created through a speaker, right? So there's some speakers at the bottom. So yeah, it actually does have both, because the parts that are played from a CD, and this actually is capable of playing in a whole orchestra, and then just the piano is sort of the solo, and it'll play the background all digitally. Now our ears are not, sharp enough to tell the difference, but basically, yeah, it's both. It's digital and analog music. Now you could make a point that, hey, when it comes out of the speaker, it becomes analog, and it's true, right? But that's what we talk about. It's like it's digital versus analog, because where is it stored, and then the quality of it that comes out. This technology is called Pianomation, and in the current version of this technology, okay, not only do they record the pianist on how hard they hit the key and how long they hold it, but they also do a video. So in a concert hall, they'll do a video of the pianist with the orchestra, with the recording what he's doing, with recording what the orchestra is doing, and then they sell it. You buy the piano, you buy the whatever recording, and a big screen TV. So then, okay, not only do you have the piano playing in your house, but you see the whole ambience of a concert hall with the pianist, with whole orchestra playing behind. Pretty cool, isn't it? I mean, you can see how technology can, influence areas that are very core analog. And like I said, in the past, you would have to learn to play the piano for quite a few years, and now you can have a Chopin right in your living room on the actual piano. It's pretty amazing stuff. All right, so that's analog versus digital, and it's just really exciting. Excellent. The textbook was talking about something else, something called towards the end of the chapter, data codes. Okay, data codes, because now we are to the point where we talked about the train. It's time to talk about the data itself, and data codes are nothing else but a way to go from zeros and ones to visible characters that we can understand. When you see letter A on the screen, okay, the computer actually sees a number behind it. So there is a very popular data code called ASCII, and when you press A, it just means a number, and then this number then can be put on the signal train and can be transmitted somewhere else. And the moment it's a number, there's no issue with modulation, with digitization, because it's all digital. So ASCII is very popular, but ASCII only has the Western characters, the main characters on the keyboard. So the Unicode is more popular today because of the internationalization of many systems. Excellent. Well, let me show you sort of the advantage of binary versus analog in a little demo. A volunteer. I need a volunteer. Someone would like to volunteer? I'll choose a volunteer in a minute. So, okay, please come, step up. And what is your name? Andrew. All right, that's right, Andrew. So, Andrew, have you ever had your mind read?
Nope.
No? Okay. All right. The head might be a little bit of a difficulty for me, but I'll work with it. No, you're okay. You're okay. No, what I will do is I'll actually show you on the screen what we'll be doing here physically. So, okay, so what I'm going to do is I'm going to show Andrew a set of cards, and these cards are basically, each section is a different card. And we have just a few sections here on this sheet. So you can actually later on go to this tweet there, and you can download and you can print if you want to. But here's how it works. You go ahead and choose any of those cards. All right, very good. And choose a number on it. And don't tell me what it is. Just a number. Is the number is on this card? Okay, very good, very good. So that's the numbers on this card. And now all I need to know is whether the number is on this card.
Nope.
No.
I believe so.
Oh, so it's fairly important.
Yeah, no.
Okay, it's not on it. Okay. How about this one?
No.
All right. How about this one?
Yes.
All right. Very good. And how about this one? Is it on this card?
Yes.
Okay, great. Go ahead and set it down. How about this one?
Yep.
Okay, go ahead and set it down. So the number you chose was, I'm getting vibes here, 23.
Yep.
All right, very good, very good. Thank you. Anybody else? Who else would like to try this? Okay, please step up. Thank you very much for that. So go ahead and choose a number on this sheet right here. You got it?
Yep.
All right, very good. How about this one? All right, how about this one?
Yep.
All right, this one? All right, how about this one?
Yep.
Okay, and this one?
Yep.
38. Okay, thank you. All right, anybody knows how this is happening? All right.
You know the cycle, or you know that if it's so much of these, if it's on one of these cards, like maybe the first three cards and some of them.
Well, if you look at the numbers, right, this is the first set, the second set of numbers, fourth set of numbers, so these numbers, they do have a pattern to them. But so let me explain how this works. First of all, these numbers represent a binary position in a digital representation of the numbers that we use, which is decimal base. So let me open a notepad here, and imagine that we choose number 11. Okay, number 11 is chosen, which means that it does exist on the first card. So that means that I can put 1 in the first binary position in the representation of the number that you selected. I'm going to ask you on this card, is the number on this card? Number 11 is on this card, which means that I have a 1 in the second position of the binary number. Okay? And then I can ask you again, is it on this set of numbers? And it is not, because all these numbers normally would have a 1 in the third position, so I put a 0 there. And then the last number is right here, and we say, is the number on this card. And it is. It's number 11. It's on this card. So we put a 1 in the 4th position. Finally, we asked about the other cards, and 11 will not be on the other 2 cards. So we end up with 2 zeros. Okay? All right. So how do we read this number? Well, the first character here is a 2 to the power of 0. That's the first number. What's 2 to the power of 0? 1, right? 2 to the power of 0. The second one is 2 to the power of 1. So if I have 1 in the first position, then I have 1. If I have 1 in the second position, then I have 2. So the total is 3 so far. Then there are no elements in 2 to the power of 3, and then there is 1 in the 2 to the power of 4. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, total 3, none for the third, and 2 to the power of 4 is 8. And then 8 plus 3 is 11. All right? Easy, right? So here's how you do that with the cards if you're not that strong in binary. When you give someone this first page, the power representation is already in the upper corner. That's 1. So you say, okay, choose the number here. You count in your head 1. Choose a number here. Oh, it's there. You add 2. So it's now 3. Then you ask, is the number here? And the response is no. And then we switch to the last one. Is the number here? Yes, it is. So you say 8 plus 2 plus 1. All right? Does that make sense? Anybody has a question about that? All right. So you can see the binary system is basically based on the answers yes or no. Yes or no. And you can come up with the answer. So I did share this link here. I shared the link here through Twitter, and so you can pick up the page, print it out, and then be a just the social butterfly and the party entertainer if you like. Okay, so now after reading minds, it's hard to top, but let's go ahead and let's look at our assignment in week 3. And this time, the assignment comes from us from a company called NetApp. Today, we talk about data. We talk about zeros and ones. Well, storage of data has become a very significant challenge to telecommunications, to technology in general. Okay? You've mentioned in our previous session that you're interested in iCloud, in cloud services. Well, the very first thing that cloud struggles with is just the amount of data that needs to be stored. If you consider maybe Amazon Web Services, where people can run their virtual machines, people can do backups, that is just a lot of data. So storage technologies have made huge leaps and bounds, and you may be familiar with a hard drive that you put in the computer, and that may have maybe a terabyte of disk space. You may be familiar with a flash drive that you plug in and store data on that, or a CD-ROM. Well, today, in an IT office, to store data, you would have something called a storage area network. And that's a server as big as a refrigerator, and all it has inside are disk drives. And these disk drives then are logically divided. There are all kinds of precautions made and resilient setup so that there's mirroring and things like that. But basically, all the storage is in one big system, so that your server doesn't have to have any drives, or it can have a small drive to start from, and then all the data that it is using, it's going to connect to the storage area network system. Now, the really cool thing about it is that those storage area network systems can do a lot of tricks on the data. For example, if you have a database that's 2 terabytes in size, how long do you think it takes to copy this? Like if you just want to do a copy, you know, you are about to upgrade and you just want to do a copy so that you can recover very quickly. Yeah, it can take hours and hours, if not days. And so what the storage area network systems do is called snapshot technology. So instead of, when you say, I want a copy of this, instead of doing a physical copy, they're going to say, freeze whatever it is here, and when the original system starts requesting this data, store only the changes they are making. And by the way, you have a copy of the data, and you can make your changes to it, and we'll save only your changes as well. See? So in just a split second, the system now allows you to have two different copies of the same data. It's really amazing how that works, because now nightly backup can be performed in a matter of seconds, whereas before it would have taken many hours, and sometimes systems would have to go down to do that. So this is what I want you to explore in this assignment, Storage Fundamentals. So you click on the login page. Make sure to open it in a new window. So you right-click, you say Open in a new window. Sometimes when you open it inside of Blackboard in a framed system, depending on the browser, things get confused. But you go ahead and log in. You will see three different systems or 3 courses that you can take. Let me see if I can log in here. Okay, so you should see the Storage Fundamentals. You should see Introduction to NetApp Projects. And do you see the data on tap? Is that what you see on your system? Okay, so you see 3 different courses, and these courses are delivered through what's called NetApp University. And NetApp is a leader in technology when it comes to storage. Okay, these NetApp systems can cost millions of dollars to install. Another company that does this is called EMC. Okay, Dell also has a product. They bought EqualLogic, and now they sell it as a storage system. But anyway, these guys are the leaders, and so you can experience how learning takes place in an IT office. So you come in the morning, you know, for work, and you find out that, hey, you're buying NetApp. Now you have to get trained on it, and this is the kind of material that you'll be going through to get trained. So you'll see some animations. It'll ask you for some questions at some point, and then you'll complete this assignment. You have 2 weeks to do this. Okay, so you have this upcoming weekend, and then the next week as well. And they say the Storage Fundamentals assignment is about 45 minutes, 45 minutes to an hour. Well, I mean, depending on how many times you'll stop it and restart it, it might vary. But at the end, you will have a screen that'll say you've completed this successfully, and thank you very much. There might be a certificate of completion. Go ahead and take a screenshot of that, save it to a picture file, and then upload to Blackboard. Okay. So what you'll do is you'll press print screen on your keyboard, then you'll go to Paint. You'll paste in whatever it is you see on the screen at the end with a success message. Then you'll save that to a file, and you can call the file anything. Save it to a file, and then inside of Blackboard, what you have to do is you have to click on the title of the assignment, and when you do, it'll give you the Browse My Computer link. You locate the picture, you press Open Submit, and that's how you'll turn in this assignment. Okay. Does that make pretty good sense? Okay, good. And you can take a look at the other courses if you have time. Today, I want to give you a little bit head start. Okay, I want to give you time to go ahead and start the Storage Fundamentals. It does involve audio, so if you do not have your own headphones, you can, I think, check them out in the Open Lab, or as you are watching this, I believe there is also just text subtitling, so you could do that, okay? But I want to give you some time to go ahead and take a look at this assignment so that you're not hurried. Does anybody have any questions at this point? Yes, Andrew, yes?
Server storage.
Yes. Not for now. Yeah, we'll get to those later on. We'll get to those later on. Okay. All right, great. Well, thank you very much for your attention and reading of the chapter. And next week we're going to talk about. Next week we'll talk about conducted and wireless media, and we're going to have a guest engineer from Sprint who will talk about types of wires, what Sprint does with wireless today, and where are they going as a company. So it's going to be an exciting delivery.